Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah rabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Rabbi shrah li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Okay, alhamdulillah. So today we are going to continue with chapter 5 part 2. Today we are going to go to basically a continuation of second degree of freedom system. So we talk about free vibration of second degree of freedom system. So today we are going to talk about second degree of freedom system. The same thing like we went through with first degree of freedom or single degree of freedom, which is we are going to talk about undamped force vibration and also damped force vibration. Okay, and then we're going to talk about a bit on torsional system and also vibration absorber. Okay, now I also included in this slide which is the slide from the textbook, but so you can refer to this later on. This is basically the same thing but different method. Here it is using impedance matrix. So I'm going to show you a bit different method to solve a second degree of freedom system with a damped and undamped system. Okay, so first thing first, we will go through or I'm going to talk about the undamped force vibration. Oops. For second degree of freedom system. Okay, so if you still remember, so we will use the same model like we used before, which is a spring and mass system, M1, M2, okay, and basically the rest is the same, which is K1, K2, and then X1 and X2. Okay, so again, using this model over here, we can basically derive the equation of motion from the previous chapter that we did, and in this case we put a harmonic force on M1, which is given as F1 is equals to F cos omega t. Okay, so we can I think I just write on the side over here, just to save space. Okay, so again we can derive the equation of motion to be m1 x1 double dot plus k1 plus k2 x1 oops, we don't have enough space here. I'll put it a bit smaller. Okay, so we can derive the equation of motion. The first one is m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 is equals to f0, oh sorry, not f0, as f cos omega t. Okay, the same thing we can derive the second equation motion. Just put a separation here. Okay, so the second equation motion we can write as m2 x2 double dot is equals to we just put everything on the side, minus k2 x1 plus k2 x2 is equals to 0. Okay, so we have these two equations of motion. So if we apply the solution for a force function, we did the same thing with first degree of freedom, but now since we are doing for a second degree of freedom, the general solution for sorry, not the general solution, the particular solution for a harmonic motion is that we'll have x1 is equals to capital X1 cos omega t, and x2 is equals to capital X2 cos omega t. Okay, so with the first degree of freedom we have just one term, but second degree of freedom we have two terms, right? Now so if we since we want to put it into the equation of motion that we derive, so we need to put a second derivative of each term. So x1 double dot is basically is equal to negative omega squared capital X1 cos omega t, and x2 double dot is equals to negative omega squared capital X2 cos omega t. Okay, so and if we put everything inside, if we substitute all of this in equation of motion, just put in different color, so we will have the first term is negative omega squared m1 plus k1 plus k2, this is capital X1, minus k2 capital X2 is equals to f, and then the second one will be negative k2 capital X1 plus negative omega squared m2 plus k2 capital X2 is equals to 0. Okay, so we put this as equation 1 and we put this as equation 2. Oops, equation 2. Okay, now and if we put everything in terms of matrix form, so in matrix form is we can rewrite negative omega squared m1 plus k1 plus k2 minus k2 minus k2 and negative omega squared m2 plus k2. Okay, and then multiply by capital X1 and capital X2 is equals to our term vector of f 0 and opposite f and 0. Okay, now if we solve the same way as we solve in the first degree of freedom system, we can continue and solve for x1, capital X1 and capital X2. Okay, so I just put a note here. Same solution, or not same, put as similar solution as first degree of freedom system. I think we did the same thing as second degree of freedom system as well. so you can refer back to the notes on that. Okay, so we can solve for capital X1. Basically we get negative m2 omega squared plus k2 times f. Oops, just put it straight. Okay, over I think we write down first. So at the denominator here we will have m1 times m2 omega to the power of 4 minus k1, oops, k1 plus k2 over m1 plus k2 over m2. Everything here we multiply with omega squared. I'll continue down here. I hope you can see this. Plus k1 is a bit long, so please be patient. m1 m2. Okay, I just put a signage here. Okay, so this is for x1. So similar thing we'll do for x2. Okay, so similar thing we'll do with x2. Put new page. Oops, I don't want to use this template. Okay, here's it. Okay, so we put another page, new page. So continuation with x2, capital X2, we'll have k2 times f divided by m1 m2 times omega to the power of 4 minus k1 plus k2 divided by m1 plus k2 divided by m2 is multiplied by omega square. And then continue down here, we'll have k1 times k2 divided by m1 times m2. Okay, I hope you can see. I'll just put one I just put a note here or a signage here. Okay, okay. Now with these two equations we can assume omega 1 is capital omega, so capital omega 1 is equals to k1 over m1, and then capital omega 2 will be k2 over m2, and our static deflection will be f over k1. Okay, so so we put everything this the term that we assume here into the equation x1 and x2. So we'll have I'll put here. Sorry for the noise at home. So again we substitute this in terms in x1 and x2. So we'll have the first term is capital X1 over xst, or static inflection, 1 minus omega divided by capital omega 2 squared divided by omega minus capital omega 1, oops, not minus, divided by capital omega 1 squared minus omega 1 divided by capital omega 1 squared and then we'll have another term times omega divided by capital omega 2 squared. I'll continue down here, not enough space, minus omega 2 divided by capital omega 2 squared. Okay, so this is the first one. Okay, again I'll put a signage here. Oops. Then for x2, the same thing, so capital X2 over xst. This one will have 1 over omega divided by capital omega 1 squared minus omega 1 divided by capital omega 1 squared multiply by omega divided by capital omega 2 squared. Again we'll continue down here, minus omega 2 divided by capital omega 2 squared. Okay. I'll put a signage here. Oops. Okay, so we have that two equation. From this, if we assume for example, if we assume m1, I'm going to show you the when we have certain parameters and we draw up the relationship between x1 over xt and x2 over xst, we'll look later on. So m1 is 1 kilogram, m2 is 0.5 kg, and k1 and k2 as well as k2 is equals to 1 Newton per meter. Okay, so if you look at here, so I have this picture over here, so or graph over here. So here is the relationship between x1 over xst and x2 over xst. So remember, x1 is where the force input is. Okay, right? X1 is where this force input is. X2 is the effect of it. Okay, so here, if you can see here, so we can draw up this relationship between x1 and st. So each line it represents the natural frequency omega 1 and omega 2, this capital omega 1 and capital omega 2, as well as this one is omega 1 and omega 2. Okay, so when the frequency becomes a natural frequency, omega 1 and omega 2, so we'll see basically the amplitude or the response goes to infinity, right? So this is where the resonance is, right? This is where the resonance is, as well as this one, and as well as this one, right? So but if you can see here, in between omega 1 and omega 2, where it relates to omega capital omega 2 over here, it becomes 0. Okay, the ratio between x1 and xst becomes 0. This is it is called a anti-resonance. This point over here, where the ratio between x1 and xst is equals to 0, where it is called anti-resonance. Okay, so and if you look at x2 and xst, there's no anti-resonance, only resonance there, and this is because the force input is only on the x1 and not in x2, so we can control better in x1 rather than x2 if you want to control in terms of the resonance itself. Okay. Oh, and I forgot to mention this omega 1 and omega 2 is actually where we derive the natural frequency omega 1 and omega 2. So omega is the general frequency. Okay. We've talked about how to derive the omega 1 and omega 2, I think, in previous session. Okay. So next we are going to go into force vibration. Okay, force vibration for a 2 degree of freedom system in terms of damped system. Okay, so the second one is in terms of what did I put the okay, so it's damp vibration for 2 degree of freedom system. Okay, so again we are using the same system as before in previous session, where I put a mass and damper system, M1, M2. Okay, so here we have K1, C1, K2, and C2. This is X1 and this is X2. Okay, so again, say that the force comes or being applied on M1, and this force is F1 is equals to F cos omega t. Okay, same thing. Okay, so again the same thing as before that we did for second degree of freedom system, the previous session, and we say the initial condition is that x 0 and there's no f2 on m2. Okay, so from here we can derive the equation of motion. So the equation of motion, the first one will be m1 x1 double dot plus c1 plus c2 x1 dot plus k1 plus k2 x1 minus c2 x2 dot minus k2 x2 is equals to I don't have enough space here, I just continue down here, f cos omega t. Okay, just put continuation here. Okay, and then the second equation of motion will be m2 x2 double dot plus c2 x2 dot plus k2 x2 minus c2 x1 dot minus k2 x1 is equals to 0. Okay, so we have these two equations of motion. Now from here, since the term if we stay with this f cos omega t, and since the x term will be applied, so if we use the normal particular solution, this x double dot will have cos omega t, right? But then this x dot will have sine omega t. So it's not possible to rearrange the equation and to cancel out the sine term. Okay, so so in that case we can use another method which is the same input for harmonic motion, which is the complex number, by using complex number. Okay, so from there what we can do is we can assume, oops, so I just put some notes here. So using complex numbers, okay, we assume the first one will be what happened? Okay, the first one will be z1 is equals to x1 plus I y1, and z2 is equals to x2 plus I y2. Okay, so using this method, and we can rewrite the equation of motion. Equation of motion. So the first one will have m1 z1 double dot plus c1 plus c2 z1 dot plus k1 plus k2 z1 minus c2 z2 2 dot and minus k2 z2. Continue down here is equals to, now here we will have the term f cos omega t plus I f sine omega t. So this we can represent as f exponential I omega t. So it's I mentioned before in the earlier class where we can represent the harmonic motion in terms of three functions. So this is the complex numbers. Okay, and the second equation of motion will have m2 x2 double dot plus c2 z2 dot plus k2 z2 minus c2 z2 dot, oh sorry, not z2 dot, z1 dot minus k2 z1 is equals to 0. So this is using complex number. If you refer to the slide, or if you refer in the textbook, it uses impedance matrix. So you can also use that method as well. Okay, so what I'm showing you is another method. Okay, now if we take the particular solution of the complex number, so the particular solution will look like this. So the particular solution will look like z1 is equals to capital Z1 exponential I omega t, and Z2 is equals to capital Z2 exponential I omega t. Oops. I omega t. Okay. And we continue to the next page. And if we solve for the if we take the derivatives, so z dot z1 dot will be I omega capital Z1 exponential I omega t, z2 dot will be I omega capital Z2 exponential I omega t, and z1 double dot will be negative omega squared z capital Z1 exponential I omega t, and z2 double dot will be negative omega squared capital Z2 exponential I omega t. Okay, so using these two equations, and we solve for the we eliminate, just put a note here, so eliminating the exponential term. Okay, eliminating the exponential term, what we will have is we will have the first one is negative omega squared m1 plus I omega c1 plus I omega c2 plus k1 plus k2. This is capital Z1. I continue down here, plus negative I omega c2 minus k2 z2 is equals to f. Okay, I just write a note here. Okay, and then the second equation is negative I omega c2 plus k2. This is times capital Z1 plus negative omega squared m2 plus I omega c2 plus k2 times z capital Z2 equals to 0. Okay, I just oops, this first equation, and I put different color. This is the second equation. I hope you can see this. Okay, so I just put it like that so that it's easier for you to see. Okay, and we can represent this in terms of matrix form. So oops. So in matrix form, we will have a negative omega squared m1 0 0 m2 z1 and z2 plus I omega c1 plus c2 negative c2. If you look at here, it's quite similar with the one that we did with free vibration, z1 and z2 plus k1 plus k2 minus k2 minus k2, and down here k2. Oops. Multiplied by z1 and z2. Okay, so here, everything here, we can gather everything. Omega squared m1 plus I omega c1 plus I omega c2 plus k1 plus k2 and negative I omega c2 minus k2. Over here we will have negative I omega c2 minus k2, and down here we will have negative omega squared m2 plus I omega c2 plus k2. Okay, I don't have enough space here. What should I do? Sorry, we just erase everything here, so because we need more space. Okay, sorry about that. Okay, so okay, so again, omega squared m1 plus I omega c1 plus I omega c2 plus k1 plus k2. Down here we have negative I omega c2 minus k2. Again, up here we have negative I omega c2 minus k2, and down here we have negative omega squared m2 plus I omega c2 plus k2. Okay, here we multiply with z1 and z2. Okay, so everything here is equals to f and 0. Okay, not pretty. F and 0. Okay, so that's better. Okay, so if we solve, we continue next page. So if we solve for common solutions, okay, so we have z1 will be negative omega squared m2 plus I omega c2 plus k2 divided by delta. We have Z2 is equals to times F. Okay, Z2 is equals to I omega C2 plus K2 divided by delta times F. So here delta is actually the determinant of the matrix M1 plus I omega C1 plus I omega C2 plus K1 plus K2 negative I omega C2 minus K2. Continue down here, negative I omega C2 minus K2 and negative omega squared M2 plus I omega C2 plus K2. Okay, I just put a note here just so that you won't be confused. Okay, so and what happened now? Since Z1 and Z2 is complex numbers, right? So we can represent Z1 again, assume so Z1 will be equals to, we just assume since Z1 is will be defined in terms of complex numbers, so it should have a real and complex part, right? Complex component. So A2 plus IB2. Okay, so then to find the response, which is Z1 and Z2, we have enough space here. Don't think so. So we need to add another page. Okay, so this will be a bit long again. So we'll have this is small z. Okay, small z1 or the response, capital Z1 exponential I omega t. So this one is the previous definition that we had. So this will be Z1. We substitute the Z1, the assumption that we put, A1 plus IB1 times, we put it back in terms of cosine and sine, plus I sine omega t, and then Z2 will be again Z2 exponential I omega t. Same thing, we have A2 plus I B2, and again the same thing. We didn't continue. Sorry, we continue. Why is it slow? Okay. Sorry about that. So we continue with this one. So the solution for this one, if we put everything together, so we will have we separate between real and imaginary numbers. So A1 cos omega t minus B1 sine omega t plus, so this is the imaginary parts, A1 sine omega t plus B1 cosine omega t. Okay, and then the same thing we do for Z2. I just do a shortcut here. The same thing for Z2. So Z2 will have A2 cosine omega t minus B2 sine omega t plus I A2 sine omega t plus B2 cosine omega t. So it's the same thing as Z1. Okay, so and since x1, so since the actual response, so I just put here, since actual response x1 and x2 are the real parts of Z1 and Z2, so we can write the response of x1 and x2. So x1, so we take the real part, which is A1 cosine omega t minus B1 sine omega t. So this one we can rewrite as A1 squared plus B1 squared, the magnitude of it, cosine omega t minus phi 1. So since this term over here is the magnitude, so the magnitude is also equals to capital Z1. Okay, magnitude of capital Z1 cosine omega t minus phi 1. Okay, which also relates to the magnitude of capital X1 cosine omega t minus phi 1. Okay, so we do the same thing. I'll just do a shortcut here. We'll do the same thing with x2, with A2 and B2, and also phi 2. So I just make a shortcut here. So this will be A2 plus B2 squared cosine omega t minus phi 2, and this is equals to magnitude of Z2 cosine omega t, oh sorry, not the magnitude, the absolute value, and this also relates to x2 cosine omega t minus phi 2. Okay, and we put phi 1 and phi 2. So tangent of phi 1 is equals to B1 over A1, and tangent of phi 2 is equals to negative B2 over A2. Okay, so so to solve for everything, and we put everything into perspective. So this is just a shortcut here, so I'll go straight to the solution for x1. X1, so that we know as absolute value of Z1. So this is actually, we can put it here, K2 minus omega M2 squared plus omega C2 squared square root over square root of E squared plus B squared. I'll show you what is A and what is B. Okay, so this is just a shortcut for it. And then x2 will be absolute value of z2 this will be k2 squared plus omega c2 squared square root divided by square root of a squared plus b squared times f. Okay. So again, we can read it with phi 1 and phi 2 by substituting b1 and a1 as well as b2 and a2. So phi 1 will be inverse tangent of negative omega squared m2 plus k2 times b minus omega c2a divided by negative omega squared m2 plus k2 times b plus omega c2a. This is the first one, phi 1, and phi 2 you can represent as inverse tangent of minus k2b plus omega c2a divided by negative k2a minus omega c2b. Okay, so what is a and b? So a here is actually the term negative omega squared m1 plus k1 plus k2 times negative omega squared m2 plus k2 minus k2 squared minus omega squared c1 times c2. And then b, the b term is omega times negative omega squared m2 plus k2 c1 plus negative omega squared m1 plus m2 plus k1 times c2. Okay. Okay, so that is for second degree of freedom, the response and the phase. Okay, so it's a bit it looks a bit complicated, but we will go through some tutorial later on. You can also take a look at the slide. There's a different method here. So this is using using impedance matrix. Okay, impedance matrix, by substituting the impedance matrix over here, multiplying with the vector of x is equal to the vector of the force. Okay. Okay, so we can also use this method. This one looks simpler, but actually you need to understand a few things first. This one you can refer back to the textbook, especially because it's written equation 5.30, but it's not here, so you have to refer to the textbook. Okay. And you can also use you refer to this example, okay, to solve it. Now, just to mention a few on torsional system. Okay, so torsional system here is basically the same method as with the mass spring and damper system that we did before, just that we can substitute. You can, if you look at the equation motion, it's similar with the mass and damper as well as the spring system. So just that we change, or we can replace J1 and J2 with M. We can replace theta as with X, and then the rest will be the same. M will be the force. Okay, so so everything in terms of the solution to find the response and everything is the same method as we did before with the free vibration, undamped forced vibration, damp free vibration, as well as damp forced vibration. Okay, so how do you derive this equation of motion for torsional system? So that one I leave it to you. Okay, so because we did this before in control system, right? So it's basically the same thing as mass spring and damper system. It's just that you have to reimagine in terms of rotational system. Okay, so okay, so you can try this example 7 and example 8. Please do it on paper, and please submit through Google Classroom. Okay, and then a vibration absorber. So so basically the continuation or the application of a second degree of freedom system is the vibration absorber. So vibration absorber, or also called as a dynamic vibration absorber, is a mechanical device used to reduce or eliminate unwanted vibration. Okay, so it's a vibration absorber, so as the name suggests, right? So usually it consists of another mass and stiffness attached to the main mass that needs to be protected from vibration. We do also here it mentions stiffness, but it's not only restricted to spring, but also including damper as well. Okay, so commonly used in machinery that operates at constant speed, because the vibration absorber is tuned to the one particular frequency, and also again the vibration absorber will have two natural frequencies, meaning you will have a better wide range of possible frequencies that will not excite the natural frequency, which will produce resonance, right? So without vibration absorber, unbalanced reciprocating forces might make the device impossible to hold or control. Okay, so what is the so here I only mentioned about undamped dynamic vibration absorber, meaning without damper. Okay, because with damper it will be a lot more difficult. Okay, so we in this course we just go into undamped dynamic vibration absorber. So based on this model here, we can describe the EOM as these two equation. Okay, and assuming that is harmonic motion, the particular solution will be this one, right? So we have, since this is 2 degree, right? So 2 degree of freedom, so we have the first one and we have the second one, so that's J1 and 2. Okay, so steady state amplitudes of the mass, we can apply the same method as before, x1 and x2. Okay, and by tuning the system to frequency of the exciting force such that omega squared is equals to k2 over m2, the system acts as a vibration absorber and reduce the motion of the main mass m0 to m1 to 0. So if we tune the system so that the omega will be equal, so this the frequency will equal to the mass. We tune the mass of the absorber, the vibration absorber. We tune it to be k2 over m2. Okay, we want it to reduce the motion of the main mass m1 to 0. So the main frequency, natural frequency, and the natural frequency for the absorber. So the equation of motion for the steady state amplitude when the static deflection delta st f0 over k1. So we can show the first one. This is the x1 over delta st. Okay, and the second one is for the vibration absorber. Okay, so so at when the frequency is at the natural frequency, amplitude x1 is equals to 0, but the absorber mass has an amplitude equals to this function over here. Okay, so because the force acting on m2 is f0, okay, we can get it from this equation over here. So the absorber system k2 and m2 exert a force equal and opposite to the disturbing force. So thus the size of k2 and m2 depends on the allowable value of x2. Okay, so and the absorber is tuned given the mass ratio. So the absorber we can tune with this equation over here, k2 max, the maximum value of the stiffness we can rely on this equation over here, and the minimum steady state we can rely on this equation over here. Okay, so this is for an undamped dynamic vibration absorber. Okay, so you can refer to this equation here, and also this equation for the parameters of the vibration absorber. Okay, so yeah, okay, so that's it for today. Sorry for any shortcomings. Please do the homework, the example 7 and this example 7 and example 8 over here, and please submit it through Google Classroom. Okay, so and thank you very much. Thank you for your attention. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'asri innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawassaw bil haqq wa tawassaw bis sabr. Assalamualaikum warahmatullahi wabarakatuh.